We've now seen the definition of a triple integral over just a standard rectangular box, kind of the most simple not being equal to easy, of course, kind of the most simple definition for a triple integral that we could come up with. If you remember, we started with saying that, okay, well, we have this rectangular box for our domain, or if it's not the domain, then it's like a restriction of the domain to just this box, right? This box will always be included in the domain at least. And then we wanted to define the triple integral of a function over this rectangular box. And we defined the integral using limits and sums, and then came up with, thanks to Fabini, we can use iterated integrals just as we did in the case of double integration. And now we want to talk about triple integrals over general types of regions, right? Not necessarily just a rectangular box. If you're doing math out in the wild, you're going to see a lot more general cases than just integration over a cube, right? So let's look at some generalized region now. So here's x, y, and z. And let's say in the xy plane, we have some sort of like arbitrary domain D, or some bounded, closed and bounded region D, right? Well, we could look at using D here, we could look at kind of generalized regions where now the bottom of our region is some function like z equals u1 of xy, because the bottom now, instead of this just being a rectangular box, the bottom of this shape could be a surface all on its own. So u1 of xy, and the top of this region could also be a surface. We'll say like z equals u2 of xy. And we could call this whole region here, we could call this region E. And now we want to define the triple integral over the region E of f of x, y, z dv, right? And so how can we do this? Well, because we're bounded in the z direction, right? Like what are our z upper and lower bounds? Well, the lower bound is the function that's closer to the xy plane, right? Which is going to be u1 of xy. And then the upper bound is going to be u2 of xy, because this height changes as your xy point varies, right? And so that means our z bounds are actually functions. So how do we describe E? Let's describe this region E, right? This region E is going to consist of points x, y, z in three-dimensional space such that, well, what do we have? We have that we're looking over, kind of, if you will, here. Let me use like green. This is kind of lifted above some two-dimensional region D here, right? And because of that, we're looking at points x, y that are in our domain D, right? We're picking points x, y that are in our domain, and then we're lifting them and saying they can be the z coordinate corresponding to this x and y point can be anywhere between u1 of xy and u2 of xy. And so that means x and y are bounded to be, are restricted to be in this region D here. And then our z value is restricted to be between these two surfaces. And so that's exactly what we have. We have the x, y is in D, and then we have that z is between u1 and u2. So I'm kind of running out of room here. I apologize for that. So that's here. We have the x and y are in D, and then we have that z is bounded between u1 of xy and u2 of xy, right? And that means we can set up the triple integral as follows. Then we can set up the triple integral over the region E of f of xyz dv. Well, then this can be the double integral over the region D, and then the integral where z goes from u1 of xy to u2 of xy. And then we'll integrate first with respect to z, and then here we have dA, right? And so this gives us a way to integrate over a generalized region here where, again, the z bounds can be functions of the variables x and y here. So this gives us a way to describe the triple integral over some sort of generalized region like this. However, this is not the only way we could set up a generalized region, right? We could also set up the triple integral for region D in the xz plane or the yz plane, right? Here we set this up with a region D in the xy plane, but there are two other coordinate planes that we can consider, and that means there are two other ways that we could consider a generalized or a triple integral over a generalized region, right? We could also do something like, let's consider we have x, y, z. Let's say our generalized region now was in the xz plane. So here are like points xz in some domain D. And then we kind of look at a lift of this, but now to surfaces above the xz plane instead of above the xy plane, right? And so we could look at this region E here. Well, in this region E here, it would have a lower y bound, right? Y would start by going from like u1 of xz to u2 of xz. And that means, like, if we call this region E, well, then the triple integral over the region E here would be something, so f of xy z dv. The triple integral here, well, now it would be the double integral over this region D, but then the height here, this height in the y direction, right? Now it's height in the y direction. These bounds, y is bounded below by some surface given by u1 of xz, and bounded above by another surface given by u2 of xc, and then f of xz, f of xyz dy, and then dA, right? And so here's another way we could set up a generalized or an integral over a generalized region. And there's a third one, right? What if we have something over the yz plane? And so here we have some domain D with points yz in D. And then we look at kind of this region bounded between two surfaces above the yz plane now, right? And so this surface in the back can be the lower bound for our x, right? So this is going to be x equals u1 of yz. And then kind of farther out of the screen, we have x is bounded above by u2 of yz. And then the height here, so the x value, the height in the x direction is bounded by these two functions. And so the triple integral over this region, E, of f of x, y, z dv is going to be the double integral over this domain D, right? And then times, or not times, but double integral of integral from x is going from u1 of yz to u2 of yz of f of x, y, z, and now dx, right? And then dA. And so there are three kind of ways that we can consider a generalized region. And it's bounded between surfaces, where do we go? It's bounded between surfaces who are functions of x and y, or it's bounded between surfaces who are functions of x and z, or it's bounded between functions who are, or surfaces who are functions of y and z. And so here you can see we get these three different kind of like building blocks for setting up these integrals. And now, to express this fully as an iterated integral, right? For now, we've only described the interior, the innermost integral, in terms of like an iterated integral that we've seen from Fubini's theorem. But if you remember from our discussion on double integrals, you can set up the double integral, like this region D can be generalized as well. And so the region D could be of type 1 or type 2. So let's look at a region D in the xy plane. Remember, a type 1 region was x is between a and b, and then y is bounded by functions of x. So like g1 of x, g2 of x, right? And then, so if D is type 1, so then we're looking back to, where are we? We're looking back to this formula here, right? And now, so we have z going from u1 of xy to u2 of xy. Well, if D is of type 1, then we can express this. So then the triple integral over the region E of f of x, y, z dv was the double integral over the region D of the integral z goes from u1 of xy to u2 of xy of f of xy z dz dA. Well, if D is of region type 1, then this is the iterated integral. Z goes from u1 of xy to u2 of xy. Y then goes from g1 of x to g2 of x, because y is bounded by functions of x, so we must set up the integral of y first. And then x goes from a to b of f of xy z dz dy dx, right? And so you get something similar if it's a region of type 2. So remember, type 2 was x is bounded by functions of y, say h1 of y and h2 of y, and then y is bounded by constants, say like c and d. Well, then the triple integral over the region E of f of xy z dv, this was the double integral over the region D of the integral z goes from u1 of xy to u2 of xy f of x, y, z dz dA, well then if D is a region of type 2, then the integral becomes integral z goes from u1 of xy to u2 of xy. X goes from h1 of y to h2 of y, and then y goes from c to d, and we're integrating the function f, and then the given order is dz, dx, dy. And so these generalized regions you can express, or the integral over these generalized regions you can express fully as iterated integrals, understanding if D is region type 1 or type 2. And we've seen in previous videos that you can express, a lot of the times you can express a given region as either type. And so if you want to switch the order of this integration, like if you wanted to flip x and y, say, you have to convert region D to where the bounds are expressed as a type 2 region before you can switch this, right? And we've discussed that before. And so Fubini's theorem tells us, yes, you can switch it, but when it's over a generalized region and our bounds have functions, you have to put in the work of rewriting the bounds before you switch it. And so again, this was just type 1 and type 2 over a region D that's in the xy plane. You have analogous formulas for if region D is in the xz plane or the yz plane. And so I won't write out the other four. And I think you'll be able to set it up just understanding how we set up these. So let's see an example. Let's evaluate the triple integral over the region E of 5x minus 3y dv, where E is the solid tetrahedron bounded by the planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. Okay, and so the plane x equals 0 is the YZ plane. The plane y equals 0 is the XZ plane, and the plane z equals 0 is the XY plane. And then so you can look at this plane now, x plus y plus z equals 1. And if you'd like to understand what this is doing, you can look at traces, right? If we look at traces, and say we use these planes as traces. Well, if x equals 0, then you have y equals z minus 1, or z equals 1 minus y, sorry. And if you have z equals 1 minus y, that means in the yz plane, you have the line 1 minus y, right? If you look at y equals 0, well, then you have z equals 1 minus x. So in the xz plane, you have the line. So this was the line 1 minus y, z equals 1 minus y. This is the line z equals 1 minus x. Then if you look at z equals 0, you have the line, if z equals 0, you have the line y equals 1 minus x. And so this is our solid tetrahedron, where you can see kind of from this angle, the backs are these right triangles here, and then the bottom is this right triangle in the xy plane, and then the side that's facing us is bounded by these triangles here. So hopefully you can see that tetrahedron. And this is our region that we are taking the integral of 5x minus 3y over, right? And so what do we need here? We need z bounds, we need x bounds, and we need y bounds. So let's look at our z bounds, right? Our z bounds are going to be the height of this tetrahedron, right? From the base to the top, right? And the top, depending on where your xy, where you're located in the xy plane, your distance to the top of this slanted roof is going to be different, right? And so notice we're bounded below by z equals 0, right? Because we're always in the octant whose x, y, and z coordinates are always positive, or non-negative at least. And what are we bounded above by? Well, we're bounded above by the slant of this roof, wherever we're at, right? And we have a formula for the slant of this roof. It's given by z equals 1 minus x minus y. And so that gives us our upper bound for z, right? And so if we're looking, then if we have our z bounds, well, then we need to find x and y bounds. How do we find our x and y bounds? Well, let's look at the x, y plane. Because now we've considered the height, kind of the three-dimensional aspect of this picture. We've got bounds that describe this. And so now what we're looking at is finding the bounds in the xy plane. And in the xy plane, you'll remember we have the equation y equals 1 minus x. And so here's our region. It's this triangle here. And we can describe this as a type 1 or type 2 region, depending on however you want to look at this. Since I already have considered y equals 1 minus x, we can write this as a type 1 region, where our y bounds, well, we have to look at the height, right? What is the height? Well, we start at 0 always, no matter where we're at on this line. We start at 0 equals 1, and then the height difference depends on the function. So we always start at 0, and where we stop at height depends on this line. And this line is given by 1 minus x. And then when y is 0, x is 1, so that means then our x bounds go from 0 to 1, right? And so we can set up the triple integral then. The triple integral over this region E of 5x minus 3y dv equals the triple integral. Z is going from 0 to 1 minus x minus y. Y is going from 0 to 1 minus x, and then x is going from 0 to 1 of 5x minus 3y, and then our order is dz, dy, dx. Okay. And now that we have this integral set up, all that's left to do is actually integrate. So if we integrate this with respect to z, well, the entire term 5x minus 3y is constant with respect to z. And so the integral of a constant is that constant times the variable. And so this becomes the integral, double integral, x goes from 0 to 1, y goes from 0 to 1 minus x. And then we have 5x minus 3y times z, where z went from 0 to 1 minus x minus y, dy dx. So we have integral x goes from 0 to 1. Integral y goes from 0 to 1 minus x. And then we have 5x minus 3y times z is 1 minus x minus y dy dx, right? Because if you plug in 0 for z, that term vanishes. And now before we can keep integrating, we have to simplify this a little bit. We can FOIL this out, and it seems like we'll get 5x minus 5x squared minus 5xy minus 3y plus 3xy plus 3y squared, and then we are dy dx. This becomes x equals 0 to 1, y equals 0 to 1 minus x, 5x minus 5x squared, and then it looks like it'll be minus 2xy because of this combination, minus 3y plus 3y squared dy dx. And now we're integrating with respect to y, right? And so if we integrate with respect to y, well, everything that's an x is a constant and along for the ride. So the integral of 5x becomes 5xy. The integral of minus 5x squared becomes minus 5x squared y, et cetera, et cetera. So let's write this. Integral x goes from 0 to 1 of, now we have 5xy minus 5x squared y. Integral of negative 2xy with respect to y. Well, the integral of y is y squared over 2. So that becomes xy squared. And it was minus right? Minus 2x y squared, yes. So minus 3 halves y squared. Sorry for going back and forth so much here. And then plus y cubed. From 0 to 1 minus x dx. Integral from x equals 0 to 1. Now we have to plug in 1 minus x and 0. So every term has a y in it. So the 0, when I subtract 0, that's 0. So all I have to worry about is plugging in 1 minus x. So if I plug in 1 minus x, I'm going to get 5x times 1 minus x minus 5x squared times 1 minus x minus x times 1 minus x squared minus 3 halves 1 minus x squared plus 1 minus x cubed dx. Now, this is all just like algebra 2, right? Or like high school algebra. To sit here and simplify this, I want you all to check me on it, but at the same time, trust that I get what you get when you simplify, and I check. Please. Is that I get 4x minus 13 halves x squared plus 3x cubed minus 1/2 dx. Okay. So again, please check me on the algebra. Double check that this is correct. And then we integrate now with respect to x. And so if we integrate with respect to x, we're going to get 2x squared minus 13/6 x cubed plus 3/4 x to the 4th minus 1/2 x. evaluated at 1 and 0. And so if we plug in 0, the whole term, or the whole thing vanishes. If we plug in 1, we're going to get 2 minus 13 over 6 plus 3 over 4 minus 1/2. If you simplify, find common denominators, etc., you should get 1/12. And so again, check, please, to see that this was indeed correct. And so, but more importantly, the important part of this example was so that we can see how to set up an integral over a generalized region, right? And here, this was type 1, so we set it up in the order z, y, x. All right, and the last thing I want to talk about is changing the order. Let's change the order of integration. So let's consider the triple integral. X goes from 0 to 1, y goes from 0 to x squared, z goes from 0 to y, of some function, f of x, y, z. And let's say we're looking at dz, dy, dx. And let's express this triple integral in the order dx, dz, dy, right? Instead of dz, dy, dx. Because depending on the function, imagine this function is like relatively complicated in the order dz, dy, dx, but if you integrate in the order dx, dz, dy, you get some really nice cancellation, or the integrals become much more manageable. And so then it's much more user-friendly to switch to, the work comes from converting to this order versus really difficult integration techniques. So first, let's look at what our region is, and then break it down into two-dimensional pictures along the coordinate plane projections and see if we can rewrite this, if we can rewrite this region in this particular order, right? And so what is this region? We'll call it E. This is x, y, z, and R3 such that, well, x is between 0 and 1. Y was between 0 and x squared, and then z was between 0 and y, if I'm not mistaken. Yes. So let's look at, so when you want to do this, you want to examine projections onto coordinate planes, right? So let's look in the xy plane. In the xy plane, x is between 0 and 1, and y is between 0 and x squared. So we have the function y equals x squared, which is just your standard parabola. And then x is between 0 and 1. And so we have this picture here in the xy plane. Let's look at the xz plane. Well, the xz plane, we have x is between 0 and 1 again. And then z is between 0 and y. But the upper bound for y is x squared, right? The y bounds depend on x squared. So when we look at the bound of y, if y depends on another variable, we have to consider that other variable as well, right? And so that means z then is between 0 and x squared. This is now z equals x squared, because the upper bound is y, but y's upper bound is x squared, right? So this region here, we have that x is between 0 and 1, and then z is between 0 and x squared. And then what about the yz plane here? Kind of drawing it a little smaller, just so it can all be on one page. Well, the yz plane, y is bounded between 0 and x squared, right? But we're looking between the bounds z equals 0 and y. And so we get the line z equals y squared, right? And then that is at y equals 1. And so here, our yz region is y is between 0 and 1, and z is between 0 and y squared. Again, kind of just by chasing our bounds around to whatever variables are in consideration. And now we have, well, so let's remember we want the order dx, dz, dy. So we want dx, dz, dy. And that means we need to write our bounds for x first. And so we need bounds for x that are functions of other variables, right? Because if we have functions in our bounds, we cannot put constant bounds first. Constant bounds are always the last integration. And so that means we need to write bounds for x. Well, we know if we write our bounds for x first, we want this height here in green, kind of, or this length, if you will, right? It's height in the x direction, but we can say that's length. And where we start depends on the line y equals x squared. Well, solving that for x, that means we're starting at y equals root y, or starting at x equals root y. And where are we ending, right? We're ending at the constant line x equals 1. And so if we want to set up this integral, I'll just write I for the integral. If we want this to be x equals, z equals, and then y equals, right? We're starting with x first, and our x bounds are going from root y to 1. And again, this is f of x, y, z, and we want dx, dz, dy. Okay. Then we want to integrate with respect to z next. But we've already integrated with respect to x, so we cannot integrate, or we cannot have x in our bounds. Because of that, we need to look at whichever description of z we have that depends on y and not x, right? Because if we've already integrated with respect to x, then our bounds, like bounds past that integral, can't have x in them. And so that means we see our z bounds, thanks to examining the yz plane, we get that our z bounds are between 0 and y squared. And then lastly, we have bounds that include y and bounds, excuse me, we have bounds for x and z, and so now we need bounds for y, right? But now, since we're integrating y last, we can't have z or x in the bounds, right? And so we have to find our y bounds that are constant. And so because of this, we get y goes from 0 to 1. Okay. Then the last thing I want to say here is about average value and volume. Okay. So the average value, which we'll call F average, is defined to be 1 over the volume of the region E of the triple integral over the region E of f of x, y, z dv, where the volume of region E is, so we'll say v of E, is defined to be the triple integral over the region E of the constant function 1 dv. Okay, and so I just wanted to end this lecture with defining average values and volumes. So we can use triple integrals to calculate average values and volumes of certain three-dimensional solids. And so this is where we'll stop for now with triple integrals in Cartesian coordinates. Next, we'll talk about triple integrals in cylindrical coordinates. And so at the beginning of the next lecture, I'll start with an introduction to what cylindrical coordinates are, and then we'll define the integration from there.